Let us now try to understand what is meant by substrate and reagent. Substrate is that organic molecule whose carbon is involved in new bond formation, and the other one is called reagent. What is a nucleophile and what is an electrophile? A reagent that brings an electron pair to the reactive site is called a nucleophile. It brings an electron pair. So nucleophile is represented as Nu minus or Nu with a pair of electrons. Nucleophile is therefore nucleus seeking, and the reaction is then called nucleophilic reaction. A reagent that takes away an electron pair from reactive site is called electrophile. It is represented as E+. Electrophile is electron seeking, and the reaction is called electrophilic reaction. Giving justification, categorize the following molecules or ions as nucleophile or electrophile. The various species given are HS-, BF3, C2H5O-, CH3 thrice N, Cl+, CH3CO+, NH2- and NO2+. So the various nucleophiles are HS-, C2H5O-, CH3 thrice N, and NH2-. These species have unshared pair of electrons which can be donated and shared with an electrophile. The various electrophiles are BF3, Cl+, CH3CO+, and NO2+. Reactive sites have only 6 valence electrons. BF3, in BF3, boron has only 6 electrons. So BF3 is considered as an electrophile. Electrophiles can accept electron pair from a nucleophile. Using curved arrow notation, show the formation of reactive intermediates when the following covalent bonds undergo heterolytic cleavage. Consider the first one, CH3SCH3. Here the carbon-sulfur bond breaks. Since sulfur is more electronegative than carbon, the shared pairs of electrons will be with sulfur. The bond breaks and it leads to the formation of methyl carbocation CH3+ and SCH3-. Now consider the second case, CH3CN. Here the bond breaks in such a way that the shared pairs of electrons is with the CN group. So we get methyl carbocation CH3+ and CN-. Now consider CH3Cu. Here copper is more electropositive than carbon, or carbon is more electronegative than the metal copper. So the bond breaking will take place in such a way that the shared pairs of electrons is with carbon. As a result of heterolytic bond breaking, here in this case we get methyl carbanion CH3- and Cu+. Identify electrophilic center in the following. Now consider the first example, CH3CHO. Ethanol, aldehyde is given here, and we know that in ethanol, carbonyl group C double bond O is polar with oxygen forming the negative end and carbon forming the positive end. So in ethanol CH3CHO, since oxygen is more electronegative than carbon, in carbonyl group C double bond O, carbon will carry a positive charge and oxygen will carry a negative charge. So carbon will be the electrophilic center. Now consider CH3CN. Consider C triple bond N. Here nitrogen is more electronegative than carbon. So nitrogen end will be negative and carbon end will be positive. Since carbon is positive, it will be the electrophilic center. Next consider CH3I. In CH3I, consider Ci bond. Iodine is more electronegative than carbon. So iodine end will be negative whereas carbon end will be positive. Therefore in CH3I, carbon will be the electrophilic center. Electron movement in organic reactions. Now consider the first case here. The electron movement takes place in such a way that it is from the pi bond to adjacent bond position. As a result of this type of electron movement, the double bond changes to single bond and the single bond changes to double bond. Now consider the second case. Here, the electron movement is from pi bond to adjacent atom. As a result of this electron movement, double bond changes to single bond and Y atom will be now associated with a lone pair of electrons. Now consider the third case. Here, Y atom is associated with a lone pair of electrons. This lone pair of electrons from atom Y will move to an adjacent bond position. As a result of this type of movement, the single bond now changes to double bond. For example, CH3Br plus OH minus gives CH3OH plus Br minus. Here Br gets replaced by OH. Now consider CH3Cl. Here homolytic bond breaking takes place, and as a result of which we get the species methyl free radical CH3 and chlorine radical Cl.